We're now going to do the math of spherical mirrors. And the first thing we have to do is we have to define some distances that we use in these equations that we have. The first one, dO, stands for the distance of the object to the mirror. The second one, which we call dI, is the distance from the image to the mirror. Two other important distances are the height of the object and the height of the image. Lastly, our focal length. Our focal length, F, is the distance from the mirror to the focal point. All five of these quantities will show up in the two relationships we're going to look at. Sometimes in the problems we do, the focal length of the mirror isn't given. What's instead given is what's known as the radius of curvature. These are spherical mirrors, so they actually have a radius like a sphere would. It turns out the focal length has a very simple relationship to the radius of curvature. It's half that. The first relationship is known as the mirror equation. It's 1 over the focal length equals 1 over the object distance plus 1 over the image distance. The second relationship is what we call the magnification equation. It says that the magnification is equal to the ratio of the image height over the object height. Now it turns out that that relationship is also equal to minus the image distance over the object distance. So any one of those three things is equal to any other thing. And both of these are going to be useful. As a matter of fact, let's go ahead and do a practice problem. Okay, a 1.50 centimeter high diamond ring is placed 20 centimeters from a concave mirror with a radius of curvature of 30 centimeters. Determine A, the position of the image, B, the magnification, and C, the height of the image. Okay, let's write down some of the information we have. We're told that our object, the diamond ring, has a height of 1.50 centimeters. We also know that the distance of that object to the mirror is 20 centimeters. And finally, the radius of curvature of the mirror itself is 30 centimeters. You can't do much with that radius. You need the radius to help you find the focal length, because that's really what shows up in our equations. The relationship there, if you recall, is that the focal length is half the radius. So that must be half of 30, or 15 centimeters. Okay, that's the one we want. This isn't much use. To find the position of the image, we're going to use the mirror equation. 1 over F equals 1 over dO plus 1 over dI. And let's go ahead and substitute the numbers. And so I'm going to get 1 over 15, and also I'm going to not use units because they're all the same units, and so it doesn't matter in the end. There will be problems where you might have some distances in centimeters and some in meters. You just have to make sure they're all the same. It doesn't really matter which units you use as long as it's the same. I got 1 over 15 equals 1 over 20 plus 1 over dI. That means that 1 over dI equals 1 over 15 minus 1 over 20. The way I do this with the calculator is I'm actually going to enter this in the calculator as 15 to the negative 1 minus 20 to the negative 1 equals. That's going to save you a lot of time and heartache. Now what that's going to give you in this case is that 1 over dI is equal to 0.0167. This is 1 over dI. This is not dI. To get our answer, I'm going to have to take the answer button on my calculator, something that looks like that, and then take it to the negative 1 power. And what I'm going to get is 60. So dI is 60 centimeters. That's our part A. Now the magnification is equal to two things. It's either equal to HI over HO or negative DI over DO. Now in our case, we don't know the height of the image, but we do know the image distance and the object distance. So we're not going to use this part of it. We're just going to set it equal to negative DI over DO, which is going to be negative 60 centimeters over 20 centimeters, which is going to be negative 3 centimeters. Now the significance of the negative sign is this is an inverted image. Okay, so if your magnification comes out negative, it's an inverted image. C, we're supposed to find HI. We said that the magnification is equal to -3, and that the magnification is equal to HI over HO, which means, doing the algebra here, HI equals magnification times HO, which is -3 times 1.50 centimeters, and that's -4.5 centimeters. Since the magnification is a number greater than 1, it's 3. When I say that, I mean the absolute value of the number is greater than 1. That means that it's an enlarged image as well, which makes sense here because our object height was 1.5 centimeters, but our image is 4.5 centimeters. It might be upside down, but it is bigger than what we started with, so this is an enlarged image. Now you notice I was just able to tell a few things just from the numbers. First of all, I know that because the magnification is negative, that we have an inverted image. I also know that because the magnification is greater than 1, the absolute value of the magnification is greater than 1, it's an enlarged image. The last thing I'd want to know, is it real or virtual? Well, that's the easy one, because all inverted images are real. All upright images are virtual, but all inverted images are real, and since this is inverted, it must be real. And I now know that I have a real, enlarged, and inverted image. We could tell all that without drawing a ray diagram. Now we're going to do this for a convex mirror, or a diverging mirror. The big difference here, the most important, very important difference, is that the focal length for a convex or diverging mirror is negative. Okay, it's on the other side, the virtual side of the mirror, and we make it negative. So here we're told that the radius of curvature of our mirror is 16 meters. And if you remember, the focal length is half of that. So that's going to be 8 meters. But because it is a diverging or convex mirror, that's going to be -8 meters. That's the important thing. If you get this wrong, you will not get the right answer. Because basically, if it's positive, you're saying it's a concave mirror or a converging mirror, and this is the opposite. The object distance is 10 meters away. Object distances are always positive. Same thing with object heights. Let's use the mirror equation. Let's plug the numbers in. I got 1 over -8 equals 1 over 10 plus 1 over di. That leaves me with 1 over di equals -1 over 8 minus 1 over 10th. And 1 over di then is equal to -0.225, which makes di, the reciprocal of that, -4.44 meters. To get these right, you have to remember the sign convention for the focal length. I'm actually going to do a chart right now just to help you keep track of these things. Okay, so the plus signs and the minus signs of these quantities can tell you a lot about your image. Now, let's start off first of all with the focal length. A positive focal length means I have a concave or converging mirror. If it's negative, it means it's a convex, aka diverging mirror. Okay, so the sign tells you what type of mirror. The object distance, always positive. The image distance tells you a couple things. Now, if it's a positive image distance, that means that it is real. It's a real image. We call the positive the real side of the mirror. So that's a real image. It also tells you that the image is inverted. And how do I know that? Because all real images are inverted. They go hand in hand. If it's negative, it's going to be a virtual image, and all virtual images are upright. Moving on to the image height. If it's positive, it means it's upright, and if it's upright, it has to be virtual. If it's negative, it means it's inverted, and all inverted images are real. Now finally, the magnification. If the magnification is positive, it means it's upright and therefore virtual. If it's negative, it means it's inverted and real. You notice nothing up here tells us if it's enlarged or reduced. The only thing that can do that is the magnification. If the magnification, the absolute value of the magnification, is greater than 1, then it is an enlarged image. If the absolute value of the magnification is less than 1, it's reduced. Take a good look at this chart. Write it down if you have to. This is how you're going to be able to answer questions about the image type from just the map.